All right, welcome everyone. Today we're just going to kind of review a few examples from Learning Outcomes PS-3 and PS-4, where we first started talking about having a function and representing it with a power series. So we've since gone on and looked at more examples on how we can do this in general with Taylor series and Maclaurin series. But we're going to look at a few examples, and this first one here, we already did it, but we're going to try it again. And this is from Learning Outcome PS-3. So this is example 3. We did this one. We'll kind of go through it again. But when we do these, especially these ones that are fractions, these rational function type things, we want to have in mind that one kind of prototype power series representation that we can use to find a lot of other power series representations for other functions. So let's just remember that. Let's write that down. And that was the special 1 over 1 minus x. And the power series representation for that was the sum of x raised to the power n, starting at n equals 0, going to infinity. All right, so that was our prototype form. This was the power series representation that we could do, and it's related to the geometric series. And as we saw in PS3, this allowed us to find the representation for, some types of functions. And they all kind of boil down to this fraction in some way. And so that was what we did in example 3 here. We were given this function, and we wanted to find the power series representation. And the key step for this, when we're given a function, and while I'm at it, I'm just going to rewrite that. X plus 4, write it as 4 plus x. Well, we'll do that in another step. Let's just leave that as x plus 4. So we're going to take this function, and the idea is break it apart. And this is what we did. X squared times 1 over x plus 4. And so when we look at this function that's now kind of just ever so slightly split apart, there's really two pieces of it that we consider. And this x squared part, that's a power function. So the whole point of doing a power series representation, whether it's, this prototype form or whether doing the more general case of Taylor and Maclaurin series, the whole point of a power series representation is that we can take a function and represent it as the sum of, essentially as a polynomial, these power functions added together. And so if we look at this first piece of this function, x squared, that's already a power function. So there's really nothing we need to do with that to get it as a power series. This is already a power function, so this is already good. So we're just going to tuck that to the side, and we're going to work with this 1 over x plus 4. We still need to worry about this x squared. It's still important, but where all the power series action is going to happen is with this fraction. So this is already a power function. We can deal with that later. This is already pretty good. What we want then is this function we want a power series representation for. And that's where our prototype comes in. And we kind of make this match up with our prototype form so that we can just use this formula, plug something in. All right, so we have 1 over x plus 4. So really this is the first step. Step 1 is to take the fraction and look at the pieces. If we have x terms on the top of our fraction here, and that's a power function, there it is. It's already a nice even integer or positive integer power function here. That's as good as we're going to get it. Really, the power series all the work we're going to have to do is with this fraction. We want to represent 1 over x plus 4 as the sum of power functions. So that's going to be the second step. Let's get a power series representation for just that 1 over x plus 4 function. So let's kind of hold on to this. We're going to come back to this, but let's just worry about that 1 over x plus 4. Let's get a power series representation for that. So again, we want to make this match. So what do we need? Well, we want a 1 in the numerator, we want a constant 1, and then subtraction sign. And it seems kind of trivial, but it helps. The way the denominator is set up is a constant minus x. So let's do exactly that. We're going to have, just reverse the order here. So 1 over 4 plus x. We want to get a negative here, so let's do our double negative trick. 1 over 4 minus negative x. And then we want that 4 to be a 1, so let's factor out a 4. And to help with that, you know, it can be helpful to write that and we want to put it with the negative. Maybe we should have done it first, but you know, it's fine. So we'll put it as 4 times negative x over 4. Just to help us see how this thing's going to factor out a 4. So we're just kind of getting a, not really a common denominator, it's just a common factor here. Just getting to help us out to see how this thing will factor with a 4. So now we can bring this 4 out. So we end up with 1 over 4. We'll put that in front. And then 1 over 1 minus negative x over 4. And so this is good. This is, now this fraction here is the correct setup. It's 1 over 1 minus the variable. And that's exactly what we have here. 1 over 1 minus the variable. So what we're going to do is we're going to take this negative x plus 4, and wherever we see an x in this prototype form, that's what we're going to plug in. So we're going to plug a negative x plus 4, or negative x over 4 in right here. So we're going to end up with this 1 over 4 in front, and then the sum from n equals 0 to infinity of negative x over 4 raised to the n. And so this is what we have. We have our power series representation now. It took a little bit of work, but now we have this power series representation for 1 over x plus 4. So now we can plug that back into our main line of work here. So we still have that x squared factor, but now we have the power series representation for this. So it'll be 1/4 times the sum from n equals 0 to infinity, negative x over 4 raised to the n. And now we want to get this as a power series, so we want to bring everything in and simplify as much as possible. So first, let's split up this n power over all the different pieces here. So we'll have the sum from n equals 0 to infinity of negative 1 raised to the n over 4 raised to the n times x raised to the n. So we have the negative became negative 1 to the n. The 4 in the denominator became 4 raised to the n in the denominator. And then we have that x to the n. Now let's bring on in the x squared. So when we bring it in, we're just going to add the exponents. So we'll end up with n plus 2. And then when we bring the 1/4 in, the powers of 4, we'll add the exponents there. So when we bring this in, we're going to have the sum from n equals 0 to infinity. Nothing's going to happen with that negative 1. But then we're going to end up with 4 raised to the n plus 1. Because we have n copies of 4 here. We have another one we're adding in, or multiplying in. So we're going to add the exponent. And then we have 2 copies of x here. We have n copies of x here. So when we multiply those together, we'll get x raised to the n plus 2. And so there's our power series representation. And we did this really in like 3 steps. So the first step was really to split this fraction, or to split the function apart into the part that really needs the power series representation. The x squared here, it's just a power function we can deal with. Then we identified the piece that we needed the power series representation for, and actually did it. So it was 1 over x plus 4, took some work, but we got the power series representation. And so then we plugged that in, we used it, and then we found the power series representation for the function we were actually interested in, the entire function. So here it goes. All right, so this is an idea that can be extended to, more complicated power series representations. So let's now go over to one we looked at in PS-4. We looked at an example there. And this is example 2. And so we had this more complicated function, 1 over 1 minus 2x squared. Again, we're thinking back to that prototype form, 1 over 1 minus x. And so we also have some calculus techniques that allow us to kind of convert this in some way into that prototype form. So again, let's just remember, we always want to have this one for these kind of specific examples where we have these fractions. We have our prototype form of 1 over 1 minus x equal to the sum from n equals 0 to infinity of x raised to the n. So if this squared wasn't there, we would be good already. We could do that. But because of this squared, we have to try something different. And what's new here is that we could potentially integrate this function or differentiate it to get it into this format. And that's what we saw. So we started with our function 1 over 1 minus 2x squared. And we did some work, and we're able to get the power series representation. So let's hold on with this, and we're going to come back and go through that again, but now let's try a slightly different version of this problem. Let's say we had x squared. So instead of, let's call this example 2, call it 2b, I guess. And so instead of a 1 on the top there, let's say we had x squared. So we're looking at this function x squared over 1 minus 2x squared. So let's start with that function. And when we have these functions, that same strategy we looked at in the first example we did today, let's break this function apart and look at the pieces. So we have this x squared piece, and then we have this 1 over 1 minus 2x squared piece. And the ultimate goal here is to get a power series representation for this function. And if we look at the pieces, this one is good. That's already a power function. That's already x squared. That's as good as we're going to get it. So this is already a power function with positive integer exponent. So this is good. That's the ultimate goal here, is we want to represent our function with essentially the sum of power functions. So x squared, that's already a power function with positive exponent. integer exponent. So this is really good. It's this other piece here. This is where we need the power series representation for. The 1 over 1 minus 2x squared. So this is what we need our power series representation for. So this is step one, is look at the pieces of your function and see which piece is really requiring the power series representation. We're going to have to do everything, but in this case, this x squared, that's already good. It's this fraction here that we have to do something with. So that would be the second step. The second step is get the power series representation, however you can do it, for that 1 over 1 minus 2x squared. So get the power series representation for this function. So now let's go back and actually do that. So step one is just identify which piece of your function really needs this power series representation. Here, this x squared, we can deal with that later. It's this fraction here. This is where we're going to try to really work with our power series representation. And, you know, why are we splitting it up? Well, technically, I mean, we could do this, try to do it directly with this function. But by splitting off this x squared and just concentrating on this fraction, this fraction is already closer to that prototype form. So, if we kind of go back, the prototype form is 1 over 1 minus x. This looks closer to it. If we were doing Taylor or Maclaurin series, well, we know to calculate those representations for a function, we would have to do the first and second and third and so on derivatives. And this x squared is already a power function. So we can always multiply that in after the fact. So even in those cases, if we were trying to find the Maclaurin series, it would still be easier to find the Maclaurin series for this function. And then once you have that, multiply the x squared in afterwards. And the reason is, again, this is already a power function. So this is already close to what we want. It's the main part here that really needs the power series representation is this fraction. So let's actually go through what was the process for doing this. Let's go through it again. So that's what we're going to do over here. So we've done this example again, but it doesn't hurt to do it just to see it. So we're going to start with our function that we're interested in. And we have this squared here is over the entire denominator. So there's really two kind of ways to get rid of that, either integrate or differentiate. And if you're not sure which one, try one, see if it works. If it gets you closer to this prototype form, good. If it takes you further away, then not good. Try the other one. So in this case, if we were to differentiate this function, we would end up with a cube down here. So that would take us further away from our prototype form here. So differentiating is getting us further away from where we want to go. So that means integrate. Let's integrate this function. Differentiation we could also use, but in that case, in this particular problem, differentiation takes us further away from this basic form here. So let's integrate this function. When we do that, what do we get? We get negative, or we get 1/2 times 1 over 1 minus 2x. Let's check that. So we could check that with a u substitution, and du would be negative 2 dx. So that means negative 1/2 du is equal to dx. And yeah, that looks good. All right, so we can rewrite, if we integrate, we can kind of transform this function into a new function, but now this new function we can actually find the power series representation for using our prototype here. So we can just look at this 1 over 1 minus 2x. Let's get the power series representation for that. So we're going to have 1/2 times the sum from n equals 0 to infinity. And then our variable part here is the 2x. We have the 1, we have the minus, so that's all good. Our variable part here is the 2x. So in our prototype form, we're just going to plug in 2x instead of just a plain old x there. So when we plug in 2x, we're going to end up with 2x raised to the n. And if we simplify this again, split up the exponent, bring the 1/2 in, we could write this as the sum from n equals 0 to infinity of 2 raised to the n minus 1 times x raised to the n. So it's always helpful to do this, especially if we're going to be differentiating or integrating, because we're just going to focus on the variable part here when we integrate or differentiate. All right, so what did we do? We started with this function. We integrated to get it into a form that was much closer to our prototype. We found the power series representation for this other function, which really isn't ultimately what we're interested in. So we have to work backwards. So we integrated. How do we work backwards with integration? That's differentiation. So we differentiate. So we're going to differentiate this power series. And the way we do it is term by term. So it's going to be the sum from... Now when we differentiate, when n is 0, we're going to have a constant term here. So the n equals 0 term, when we differentiate it, is just going to become 0. So our sum here is going to be from n equals 1 to infinity. And then we'll have the 2 raised to the n minus 1. And then it's just basic power rule here. So bring down the n, keep x the same, subtract 1 from the exponent. So that's just our derivative power rule. All right, so there we go. There's our power series representation for this. So this 1 over 1 minus 2x squared, here's our power series representation for that function. Now this isn't our answer because we ultimately want to do this x squared over 1 minus 2x squared. So we did this completely separate. And now we're going to plug in the result. So we went through and did this, found this power series representation for 1 over 1 minus 2x squared, completely separate from that x squared. Once we had that result, now we're actually plugging that in. So really the power series here, we did that separate. That was like step 2 to get the power series representation for just this. So notice when we went through our work, we kind of put this x squared, it's still here, but we put it off to the side for a second. Keep it in mind, but we're not actively using it. So nowhere in this work here did we have that x squared. You know, we're just working with that fraction to get it into a form that we could get the power series of. And so we had to go through some work here to get that power series representation, but we could do it. So now in step 3, we're ready to simplify this. And so we plug it in, we take that power series we found, we plug it in, so now we're going to account for that x squared. And we can multiply it through, bring it on in, so we get the sum from n equals 1 to infinity of 2 raised to the n minus 1 times n times x. And then when we bring the x on in, we're going to add the exponents. So this is going to go up to n plus 1. And so there's our power series representation for this function here. So here's our power series. This is it. This is our power series representation for that function we were interested in. So again, when we have a function that we're interested in getting the power series for, if there's a power function that's kind of mixed in there, especially in the numerator, like an x squared, it's a positive integer exponent there. So x squared, x cubed. That's pretty good. So just get it out of there. Worry about the other stuff that's more complicated. Get the power series representation for that. And then once you have the power series representation for that more complicated piece, plug it in, and then you can do what you need to with that x squared. So in this case, we essentially multiplied that x squared right on through and distributed. So that's kind of the key idea here for these power series representations, where there's a little bit more going on, is we can really split these up. And so you can split them up just like we said, where you have this power function, nice positive integer exponent here. Split that off. We can multiply it in afterwards. Get the power series representation for the more complicated piece here. Once you have that, then you can bring that x squared right on through. So this would even, be applicable for, say, a Maclaurin series. So if we were trying to do the Maclaurin series for this, for this function, probably what I would try is split off the x squared, get the Maclaurin series for this, and then once you had that Maclaurin series, then you can, put it in, and then you can keep going with the x squared there. And actually, this is the Maclaurin series. So, finding this power series representation, because it's centered at x equals 0, this is the Maclaurin series. So we actually did find that. So this strategy can be useful for, doing Taylor series, doing Maclaurin series. If you can get this power function, factor it out, you can really concentrate on getting the power series representation for that more complicated piece. All right. So hopefully that just clears up a few of the questions from the homework. Really, it's just you have to combine a couple of the ideas from what we did in PS-3 with what we're doing in Learning Outcome PS-4 for these power series representations. All right, so that'll be it. And next time we're going to be moving on into this will be the end of power series and series in general. We're going to be moving into parametric equations and polar coordinates. So that'll be for next time. We'll see you then. Bye-bye.